So today, welcome to statistics seminar, and today we are very delighted to have Richard Guo from our department to give talks about possible causal effects, enumeration, and estimation. Thanks, Richard. Welcome, Richard.
Okay. Yeah, thanks, Yanqi, and it's my pleasure to present this joint work, very recent work with Emma, and it's about observational studies, and it's about enumeration and estimation of all the possible causal effects. All right. Okay, so the talk, as the title suggests, will consist of two parts. The first part would be non-parametric. So that would be concerning the problem of how do you enumerate in an optimal sense all the possible causal effects when that causal effect is not identifiable. So we consider observational studies with no latent variables. Oh, by the way, I should say that if you have any questions, please post to the Q&A, and Emma is there, and I'm sure she's happy to answer them. And if necessary, she will unmute you, and you will have a chance to speak. Okay, so you can either type or just speak out for the questions. All right, I'll continue. So for observational studies with no latent variables, the set of possible intervention distribution, and hence the set of possible causal effects can be become optimally set identified. So that's the first part. The second part would be the natural next step, essentially. So having identified all the possible causal effects, how do you estimate them? So we will develop some efficient estimation, a very simple estimator, which is efficient in some sense, where we'll elaborate to estimate every possible causal effect. But to do that, I have to introduce some linearity assumptions such that this can be estimated. This boils down to numbers and can be estimated efficiently. All right, I'll start with the first part, enumeration. So consider a causal DAG, and I call that G naught, and it's on V. V is the set of vertices. And we all know that the observation distribution should factorize according to this causal DAG. What that means is that the joint density, for now, for this talk, we will assume that all the variables are continuous. So there is a joint density. So the joint density can be factorized. So basically, each vertex has a factor. The factor is basically a conditional distribution of that vertex conditioned down its set of parents. So I will use this as our run example. So we have four vertices, A, B, C, and Y. You can think of this A as some treatment, as some Y as the outcome. And according to this DAG, the joint density would factorize into four factors. So Y conditioned on the parents A and C, A conditioned on B, C conditioned on A and B, and finally the margin of B, because B has no parents. All right. So nice thing about this formalism is that the causal DAG also defines the intervention distribution. So technically, this intervention distribution, I would say, it is a kernel. So it takes the left-hand side. So it is a joint density on the set of vertices, which you do not intervene on, but conditioned on this do operator. So do operator is to set the set of x's to the particular values of little x's. And this formula also has a factorization form. It is called truncated factorization. So it's basically, you factorize into the factors, each corresponding to the vertices that you don't intervene on. And still, it is the value for V conditioned on set of parents, with the only condition that when you set the value little x to the big X, whenever the x appears on the right-hand side, you replace with the value x that you have imposed. So here is an example. So the way I would think about it is that when you intervene on a variable a, so here I intervene on variable a and set it to value little a, I'm going to detach the edges into the vertex a, then I'm going to run this factorization in the same way. But whenever I see a, I replace the a with its imposed value a. So it's still factorization. So it is clear from this representation that if you happen to know the true causal DAG, then the intervention distribution, this P of Y due of A, can be identified from the observation distribution. So the reason is that every factor can be identified from the observation distribution, because the intervention are only concerning the particular evaluation of those factors, it is going to be identified from the observation distribution. Okay, so the intervention distribution in general is a kernel because you can set arbitrary values to those A's. So it is a conditional kernel. All right, so now we have to worry about the question that how much can we learn the underlying DAG from observational data? So we will consider causal inference from observational data under the assumptions, the two assumptions. The one is causal sufficiency. There is no latent confounding and no selection bias. So what that means that you haven't, well, I guess the selection bias is something that you really have not conditioned on anything downstream. And low latent confounding is the common way we describe causal sufficiency. I guess it means you have measured every variable basically. So every variable is represented in the graph and you have measured them. Okay, the second assumption is faithfulness, meaning that there is conditional independence if and only if there is a d-separation in the true causal DAG G0. So Markov is to say you can, for every d-separation in the causal DAG, there is a conditional independence. So conditional independence can be derived from the factorization I showed on the first slide. And faithfulness is to say the observation distribution doesn't have any more conditional independences. It has those and just those dictated by the d-separations in the graph. All right, so then we can see that the DAG G0 is typically not identified from observation distribution for the simple reason that there are usually more than one DAG that can encode the same set of conditional independences. So here, example, the difference is between these two is just the orientation of some edges. But you can see that both of them are missing the edge B and Y. And they encode the same conditional independences. B and Y are independent conditional A and C. They have the same skeleton, or if you remove the directions, that becomes a skeleton, and they have the set of unshielded colliders. Okay. In this case, there's no unshielded colliders. So, all right. So, since they encode the same set of conditional independences, so we can only hope to learn from observation data that a representation that is equivalent, it is up to the set of conditional independences. And we call this a Markov equivalence class. So the two DAGs are Markov equivalent if they encode the same set of conditional independences. And the graphical criteria for that is that they are Markov equivalent if they share the same skeleton as the same V structures. Here, V structures means unshielded colliders. Every Markov equivalence class can be uniquely represented graphically by something called a CPDAG. It's a completely partially directed acyclic graph, or originally called an essential graph by Anderson, Madigan, and Perlman. So here is our causal DAG. Then the Markov equivalence class of that causal DAG, it is represented by this CPDAG on the right. So I'm going to take the skeletons and I'm going to see if there is any unshielded colliders. In this case, no. So it's just the skeletons. If there's any unshielded colliders, I'll put them into the CPDAG, and then I need to do an extra step of make orientations, which I will show you later. But after which, you will obtain the CPDAG that basically indexes the equivalence class, the Markov equivalence class. Okay, so it's clear that from observational data, we can only hope to learn this CPDAG. So after you obtain the CPDAG from observation data, say, then you can, if you want, you can add some additional background knowledge on extra orientations. So for example, if you have learned the CPDAG in such a fashion, and you also happen to know A is some exposure that precedes Y temporally. So the direction could only be A directed towards Y. So I could incorporate this background knowledge by orienting this edge as A towards Y, and then I will have to complete. By complete, that means just by introducing this additional orientation that could also imply other orientations, which I will show you later. But there are a set of rules that you can execute them until you couldn't execute anymore, and that would have exhausted all the implications. So in this case, there's no implication. So you will just obtain this object, and this object is called an MPDAG. So MPDAG is basically a CPDAG plus additional orientations that you know from background knowledge or expertise, and then you complete by the make rules, and you get this object. It is still, it represents a collection DAGs are compatible with this graph that is MPDAG, maximally oriented, partially directed acyclic graph, okay? Cool, so these are the 4 rules proposed by Meek, and he also showed those are sound and complete. So these rules can be understood as basically try to see the implications of an introduced orientation such that it does not add new V structures and it does introduce any cycles. So all the rules can be understood in that way. So no new V structures and no new cycles, and then a certain other orientation can be implied by just inspecting any motive on the left-hand side of those 4 rules. When you see one, you just replace by one on the right-hand side. And then you just keep doing this until there's no rule can be applied in the graph. Then you obtain an MPDAG. That's what I mean by complete, right? So, so suppose that's all the structural information we know. We denote this MPDAG by script G, and let brackets G denote the set of DAGs that are represented by this G. Now the question becomes, what we know the true causal DAG lies in this bracket G class, but the question is, can we identify this intervention distribution from observation distribution P? So as you would probably expect, the typical answer is no, because there could be more than one ways, there could be more than one DAGs, and meaning that there could be more than one ways to factor. And consequently, there could be more than one ways to write the intervention distribution. But when we get lucky, then sometimes this intervention distribution can be uniquely identified from P. That's because all the DAGs that is an element of this bracket G has the same way of identification. So here's an example. So suppose the MPDAG we have is the guy on the left. So A, Y, Z, A pointing to Z, A pointing to Z and Y, and Y, Z and Y are connected by an undirected edge. Then it has 2 instances of DAGs. So Z pointing to Y or Y pointing to Z. In the first instance, Z is a mediator. And in the second instance, Z is a common effect. So in both cases, you don't have to worry about Z. So you can marginalize over Z, you get the intervention distribution. It is just a conditional distribution of Y conditioned on A without worrying about Z. So in some cases, we do get lucky, and this can be identified. So there is this wonderful theorem from Emma that gives you necessary sufficient condition for this to be the case. So this is a graphical criteria. So the intervention distribution can be uniquely identified from the observation distribution if and only if every proper possibly causal path from A to Y starts with a directed edge in G, G meaning the MPDAG. So, okay, I'll parse it a little bit. So A here is a treatment, Y is the outcome. You can think about Y just being a real variable, and A could either be a real number, in which case that is a singleton or point intervention, or a vector, a multivariate vector. Then A would be a set of vertices, and the type of intervention would be called a joint intervention. So every proper, so what is proper? Proper means the path has only its first vertex in the set of treatments A, meaning once you exit the set of A, you never come back again. Okay, so that what proper means, possibly causal, meaning that, that deserves some explanation, meaning that the path can be oriented as all the way directed towards Y. When you draw such an orientation of that path, that doesn't create any cycle in the graph. So, okay, so let's inspect whether our example satisfies this criteria. So this is A, this is Y. A is a singleton, Y is singleton as well. And A towards Y is a path, but it's not what we worry about because it starts with a directed edge. So this is fine, but there are other two paths, ACY and ABCY. So ACY is going to cause problem because it is proper because only A is in A. It starts with undirected edge, and it is possibly causal because I can orient this as A towards C, C towards Y, but doesn't give me a cycle. Doesn't give, by cycle, I mean directed cycle. It doesn't introduce a directed cycle. So the same argument for ABCY shows that ABCY is also cause problem because I can orient the path as A towards B, B towards C, C towards Y. That doesn't cause a cycle, and yet it starts with an undirected edge, A and B. Okay, so in this case, we know the intervention distribution cannot be uniquely identified from P. So to proceed, we can think about this simple idea, maybe, that, well, it's not uniquely identified, but we know there could only be finite number of them. So I can just tell you a set that the set contains the truth. So I call this set all the possible intervention distributions and henceforth all the possible causal effects. So the idea, so the naive thinking of this is that I can enumerate all the DAGs in this class, bracket G, and identify for each of the DAG, because we know for each of the DAG, it is going to be identified. But this idea quickly becomes prohibitive because computationally it's not affordable when you have more than few vertices. So there is this interesting computation from Gillespie and Perlman that basically shows, well, they show for Markov equivalence classes, but they did the computation up to 10 vertices and they enumerated all the equivalence classes, and they found out that most of the equivalence classes are rather small, but some of them are huge. So on the extreme, for example, if you consider the complete graph, that equivalence class would contain V factorial DAGs, that because every permutation would correspond to a DAG. So if you have 10 vertices, that would evaluate to 3 million. So that's not going to be tractable computationally. So there's this very clever idea that try to enumerate a smaller set of objects, that is the set of parents of A. So when A is a singleton or point intervention, then it's just a parent setup for that particular vertex A. So that's kind of the pioneering work that started all this line of thinking. It is called the IDA algorithm developed by the researchers from ETH. And Malouche is an advisor of Emma and also a graduate from a department. So when you have more than one treatments, that would entail enumerate all the combinations of parents for vertices in A. And they extended the previous algorithm to this case, and it is called a joint IDA algorithm, was by Pratham, Malouche, and Thomas. You see many names from our department in this talk. But these two algorithms are nice, but they have a problem in the sense that the enumeration in some sense is not optimal, because the IDA algorithm could tell you, hey, there are 4 possible effects, but actually there are only 3. And basically, the set of parents is not going to uniquely index this map from the observation distribution to the intervention distribution. So you could have replicates. But this duplicate is going to be problematic when you have sampling variabilities. For example, when the algorithm reports you 4 distinct estimates, actually 2 of them could be estimating the same quantity. They just look statistically different, but they are actually estimating the same thing. So it's a little bit bizarre, I think, if the result has this eccentricity. So this motivates the following consideration of optimal enumeration. Okay, so for MPDAG G, so we want to construct a partition of this MPDAG class, basically. We want to look for sub-MPDAGs, let's call them G1 up to GM, such that it is a complete, meaning the set of DAGs represented by G can be represented as the union of the each class represented by each of the GIs. And this symbol dot union meaning disjoint union. So basically means each of the GI brackets, they are disjoint, and the union of them would be exactly G bracket. So that's a complete partition. The second, of course, is that the intervention distribution is identified uniquely under each of the GIs. And third one is crucial, is minimal, meaning this map from the observation to the interventional are distinct under each of the GIs. You can think of this as the identification formulae are different for each of the GIs. This would also imply that if you take the intervention distribution and you take expectation and you take the derivative with respect to the treatment, you get this effect. That will also imply that the causal effects are generically distinct functionals of the P. So it's clear that to do this, we have to worry about, essentially, by Emma's result, that we have to worry about the undirected neighborhood of A. So basically, we have to worry about the violators of the graphical criteria, which would correspond to undirected neighborhood of A, such that there is an proper possibly causal path from that undirected neighbor to Y. So we have to kind of orient them to eliminate them such that this graphical criteria gets satisfied. So the natural thinking would be to recursively orient the undirected edges attached to A. So let's consider a template for the algorithm. So an input would be an MPDAG G. Y is the outcome, and A is the set of treatments. I'm going to look into, pick an undirected neighbor of A. So A1 is an element in A. So A could be a set. So A1 is an element in A. I'm going to look into a undirected neighbor of A1 such that A1 is in A, of course, and there is a proper possibly causal path from this V1 towards Y. Then I'm going to bifurcate. I'm going to bifurcate into 2 different orientations for this particular edge, A1, V1. So on the one branch, I'm going to orient as A1 towards V1. On the other branch, I'm going to orient V1 towards A1. Of course, I have introduced new orientations. I have to complete them by the make rules. So this notation MPDAG GR means I'm going to add orientation to this G and complete by make rules. Okay, then I get 2 MPDAGs G1 and G2. So if the effect is already identified on any of them, I'll stop there. Otherwise, I'll just recurse. I just recurse the first step on that graph. So I think that should make sense, right? Okay, so let's try it out on our example. So this is our example, the MPDAG. So the undirect neighborhood of A consists of B and C. So that's edge AB and edge AC. So apparently we have to choose someone to start with. So let's choose AB. So if I orient AB, they bifurcate, and I try to complete by make rules, but there's nothing to do. So I'll just further orient the edge AC as either A towards C or C towards A. So there are 4 combinations. All right, so you can check that every one of them at the terminal, the effect is identified. But there is a, oh no, not yet. Okay, I'm going to compete by Meek rules, sorry. I'm going to compete by Meek rules. Okay, so let's try this as example for explaining the Meek rules. So I have introduced the B towards A and A towards C. So what does that imply? That would imply that B has to be directed towards C, because otherwise C towards B would induce a cycle BAC. So that's not allowed. So B has to directly towards C. Then you could also notice that C has to be directed towards Y, because otherwise, if I have Y towards C, then I have introduced a new unshielded collider, BCY. So that's also forbidden. So the only possibility would be B towards C, C towards Y. So if you do Meek completion for every one of them, you get those 4 MPDAGs on the terminal, and the effect is already identified on each of them. But there is a problem that if you look the 2 ones in the middle, that the difference, of course, the major difference is the direction of AB and BA. But if you take the union of them, it turns out to be MPDAG. And what's worse about it is that if you look at this MPDAG, it already satisfies that graphical criteria identification, because the only thing I have to worry is the path A, B, C, Y, but that path is not going to be possibly causal because I already oriented C towards A. Then that means I don't have to worry about it. It satisfies that graphical criteria because there is no possibly causal proper path from A to Y that starts with an undirected edge. Okay, so basically I have duplicates here. So at first sight, this seems to be a combinatorial problem because that seems to depend on how I choose to orient the edges. So the order I choose to orient the edges seems to matter. To convince you of that, so let's say we orient AC first. So we bifurcate into A towards C, C towards A, and there is additional implication of C towards Y by Meek. Then this is just that. So I'll stop here for the lower branch. I'll further bifurcate the upper branch into 2, and they are all identified. So in this case, I have 3 outcomes, each of them identified. So the lesson kind of learned from this example that it does seem to matter that the order to which you orient the undirected neighborhood. Essentially, Emma made this observation that this could be sorted because essentially what's going on here is the status of the path ABCY depends on the status of the path ACY. So if C and A is oriented such as C directed towards A, then that eliminated the possibility that ABCY, the other path, being possibly causal. So if I can sort out this dependence and try to first orient the edges that the other paths depend on, then I should get a minimal solution. Okay, so that is the idea for the algorithm. So the only modification I make here is that I have to carefully choose the edge that I pick to orient. In this case, I have to choose the undirected edge such that A towards Y is a shortest proper possibly causal path from A to Y, and just that. Then I recurse. And we can show that then the set of outputs by this algorithm is complete and minimal. I think it's easy to see it's complete because we haven't lost anything. But it takes quite some effort to show that it's also minimal, meaning that the map from the observational to the interventional are distinct for all of the outputs. All right, so semantically, what each of the GI represent, you basically represent the minimal set of additional orientations that you have to know for a particular intervention distribution or possible effect. Okay, So this also reveals a problem with the IDA algorithm I just mentioned, because if you run the IDA for this, it will run into this problem, because if you look at the 4 outputs on the terminal, because the IDA algorithm enumerates all the set of parents for A, if you look at the set of parents for A, so the first graph, the set parent for A is empty set. The second one is just C. The third one is B and C. The fourth one is just B. So they are all distinct. So IDA algorithm would enumerate 4 of them, while actually the minimum number is 3. So IDA algorithm would just give you a pair of duplicates where actually they should be the same thing. They should be, although numerically they seem different, but they're converging to the same thing. All right, so I'll pause for a few seconds to see if there are any questions from the audience.
Just curious, Richard. So what if I think you mentioned that the reason you start with the shortest path is that you may have ordering issues, but what if there are 2 shortest paths, like they have equal length?
Oh, so pick anyone, okay. Doesn't matter, pick anyone. Is there any other questions from the audience? Okay, otherwise I'll proceed to the second part of the talk. Estimation, all right? So now we have done this work that I enumerated every possible intervention distribution. So naturally, the next step, I want to estimate every possible causal effect. So I'm going to write down the intervention distribution for each of the identified sub-MPDAGs and take the derivative. That becomes the causal effect. But in general, as you can see from the definition, that this is going to be a function, because you take the derivative, but the derivative depends on where you take the derivative. It depends on the exact value of the little a. So this is an infinite dimensional object. So you don't have root and rate of estimating them non-parametrically. And they also seem to be too complicated for most of the cases, because typically we would just like simple summaries. We would like numbers instead of those functions for a lot of situations. So the simplest way to do this is that we can assume linearity. So if this map from A to the interventional expectation is linear, then if you take the derivative, of course, it's going to be a constant. It doesn't depend on where you take the derivative. And it is just going to be our vector of length, the cardinality of A. So it's just the slope of that linear function, basically. The satisfying, so tau can also be interpreted as this property. Basically, the ith coordinate for tau would be if I keep all the treatments the same level, but I just increment the ith treatment by a unit, then what's the expected increment in the outcome y? So that's just the intuitive interpretation for this total effect. So I'm going to call this vector the same length as A as the total effect of A on y. Okay, so that's going to be my estimand. Okay, so one simple way, or the way to assume this linearity is to assume that the real data, the observational data, is generated from a linear structural causal model with independent errors. I abbreviate this as LSCM/IE, associated with the true causal DAG G0. So that means the X, okay, so I'm switching notation here. So because I want to be explicit about the set of V's, actually is a V-dimensional random vector. So I'm going to use big X denoting that random vector. I'm going to use the X subscript to denote the corresponding coordinates of that random vector. So basically that says for each vertex on the DAG, on the true causal DAG, it is going to be a linear combination of its parents plus a random error. And that random error is going to be independent across the vertices. That's it. I don't assume the errors are Gaussian. The errors could be arbitrary as long as they're independent across vertices and they have mean zero. So the mean zero assumption does not add any difficulty because you can incorporate an intercept, but intercepts are going to be ancillary, so it doesn't really matter. Without loss to generality, I can assume they have mean zero. And of course, finite variances, because we are going to talking about efficiency, so they better have finite variances. All right, so so this is essentially a parametric model because the model is determined by the lambda node. The lambda node has zeros corresponding to the missing edges in the true causal DAG and the set of laws associated with those errors. What I want to say is that by assuming this linearity, in general, we don't gain anything from identification, basically. We can, when errors are Gaussian in particular, I can only still identify G naught up to the equivalent Markov equivalence cost. So it is only when you make extra assumptions about the errors, for example, the errors are going to be non-Gaussian, then there is this little magical algorithm, lingam, that you can actually identify this G naught directly, but that's only when you put extra assumptions on the errors. Otherwise, you don't. Otherwise, we're still playing the same game, basically. All right, so without assuming the type of error, we only know this true G naught is contained in the MPDAG class. And because this MPDAG class could have multiple DAGs, I mean, even for one, for multiple DAGs, and even for one DAG, actually, there are more than one topological ordering associated with a DAG. So this lambda node, because it depends on the total ordering, it's not going to be identified. So this slide is basically saying we're still playing the same game, even though we have assumed additional linearity. As long as we don't assume anything on the errors, we're still playing the same game. And I'm going to run my enumeration algorithm, and I get a set of MPDAGs such that the effect is identified on each of them. So I'm going to consider estimation on each of them. So for now, let's just consider tau, for example, under G1, G1 being the first output of the algorithm. The tau is identified under this G1. Okay, so to proceed, there is an important concept to be introduced, that is buckets. So what are the buckets? It's very simple. It's just, so for this G1, this sub-MPDAG or MPDAG, it has both direct and undirected edges. If you just look at the undirected edges and you take the maximal connected components of them, then you get this bucket decomposition. So if you just take undirected components, then naturally they partition the vertices into the components. So in this case, A, B, C form the bucket 1, and because they are undirectly connected. And Y by itself forms bucket 2 because it's a singleton. I want to say that those maximally connected components, the buckets B1 up to Bk, in this case k equal to 2, they induce, there is a topological ordering among them because there are directed edges that traverse in between those buckets, and they determine a partial ordering or topological ordering that of those buckets. So I'm going to assume that the arrow is only pointing from the lower numbered buckets to higher number buckets. Okay. Another thing which is quite important, it turns out, for our work is this restricted property. This purely stems from that we're working with MPDAGs. So what this says is that if you look at two vertices and they are in the same bucket, then if you take the parents of one vertex, but excluding those parents already inside the bucket, then it has to be the same as the set of parents of the other node excluding the internal vertices of parents. So what should I say is that the set of external parents external meaning excluding those parents inside the same bucket, are going to be the same for each of the vertex inside the same bucket. So if we look at A, B, C, well, trivially this is true because none of them has, well, A has a bucket, A has a parent, but it is already inside the bucket. So none of them has any external parent. For Y, this is also true because it's a singleton, but in this case, the external parents set for Y is A and C. Is that clear? So I'm introducing this notation parents of bucket to explicitly mean the set of external parents for any vertex in the bucket because they are all the same for the vertices in the bucket. Okay. So all right. So there is this proposition. So what this proposition serves is basically a reparameterization. As I mentioned, that this data generating mechanism is underlying, but we don't get to see the lambda 0, the lambda naught and epsilon naught uniquely because it's not identified. So I have to somehow reparameterize things such that the law is going to be uniquely indexed by some elements, by some objects. So here is a proposition that does this, that basically says, if you divide nodes into those buckets, then there is this block recursive representation of the data generating mechanism of observational data, of course. So that means each of the bucket is a linear combination of the external set of parents for that bucket plus a multivariate error. So this error could be a multivariate, and this error is a random vector, has the same length as the cardinality of the bucket, and satisfy those conditions. So the first of all, the errors inside each bucket could be correlated, but we require the errors among those buckets. So those are random vectors. They are mutually independent and of course mean 0. And each of the epsilon bk, so that's the errors for bucket k, is marked up to the within bucket subgraph of that bucket. So what that means is that if you take the subgraph associated with that bucket is some PDAG, then the epsilon bk has to factorize according to some DAG that is represented by this PDAG. So the PDAG is taken to be the subgraph induced by the bucket. The third one is that the red edges, in this case, I draw the red because they are traversing between the buckets, the between bucket edges. So the between bucket edges determine the sparsity pattern in this lambda. So the lambda only has non-zero entries on corresponding to those between bucket edges. Okay, I hope this is clear, but basically this is a reparameterization that says the observation distribution can be represented by this block recursive form such that the errors associated with each bucket allowed to be dependent within the bucket, but they have to be independent across the buckets. Okay, so in this case, to write down what this entails would mean A, B, C, they're just equal to, because they don't have any external parents, just equal to the errors, epsilon A, epsilon B, epsilon C. These three could be dependent. And Y is going to be a linear combination of external parents, in this case, A and C. So it would be the lambda times the corresponding XA and XC plus an epsilon Y. As I said, the errors across the buckets has to be independent. So epsilon Y is independent of this random vector epsilon A, epsilon B, epsilon C. Okay. All right. So having done this reparameterization, I can basically use this result from, I guess, the same paper from Emma, that write down the intervention distribution. So D is a set of nodes that is determined to be the set of ancestor Y, but in a graph that you remove the set of treatments. In this case, if you remove A, and Y is just connected to C, and the set of ancestor Y is just to C and Y. So in this case, D equal to C and Y. But basically, this is just a formula that you can apply this definition and specialize, if we specialize to the linear structure of causal model with independent errors or this reparameterization that I just introduced, then I have a simple identification formula for this total effect, basically. So the total effect can be expressed as a function of this lambda. Remember what is lambda? Lambda is this coefficients that determines the between bucket relations. Okay, so it only involves the between block, by block I mean bucket, I should say bucket, only involves between bucket coefficients in the block recursive representation. And in this example, tau just equal to lambda. If you apply this formula, it's just equal to lambda of ay. Here, it's just equal to that. Okay, so I'm going to develop an estimator for this. A natural idea is that if you have good estimates for this lambda, then you can just do a plug-in and you can estimate this tau. As a stepping stone, I can think about if error is a Gaussian, how to do the MLE for this lambda. If I plug in the MLE for lambda, I get an MLE for tau. So hence, that would be the most efficient. So I'm going to write down the Gaussian likelihood, and I'm going to maximize with respect to the, so in this case, the model is parametric, lambda and the covariances for the errors. But the covariances for the errors has to satisfy the Markov property with respect to the per bucket MPDAGs, basically. That's going to impose some zero conditions on the inverse covariance. So in general, this is like fitting an MLE for a Gaussian chain graph under what is called an alternative Markov property. In general, there's no closed form solution, and as you have to use some specialized algorithms, such as those proposed by Dorton and Eichler. But however, it turns out because of this restrictive property, we can show that we have a very simple solution in this case. Just we get lucky, and we have a special case where lambda k can be estimated just as the least square coefficient of regressing the bucket bk onto the set of external parents. It just least square coefficients, nothing more. So it's quite surprising that the constraints in this case on this omegas play absolutely no role in estimating this lambda case. There is a discussion on the similar phenomenon by this old paper from Anderson. Okay, so I can call this estimator, I'm going to call this estimator the G regression estimator, tau G hat. So that entails regressing each bucket onto its external parents with least squares, and then plugging into that formula for tau. Okay, so it's clear that if error is a Gaussian, then it tends to Kramer route bound. But what if error is a non-Gaussian? So it would not attain semi-parametric efficiency bound in general because, well, I could construct some other estimators that are going to be more efficient. For example, I can construct an estimator by estimating the error distribution because errors are unspecified. I can estimate the score for the error, and then I can hopefully construct a more efficient estimator. But that seems to be too complicated for practical uses in general, and not going to be very stable because you try to estimate the error scores. But still, I suspect, or my conjecture is, this G regression might still dominate a lot of other estimators in the literature. Although it's not going to achieve the semi-parametric efficiency bound, but it could be more efficient than most of the other proposals. So that would include the adjustment estimators. So what adjustment means, that was the content of Emma's job talk, but basically you regress Y on the treatment A and a set of adjustment covariates, and then you read off the coefficients on A, that is the estimate for the total effect of A. But there is more than one choices for those adjustment covariates usually, and some would be more efficient than the others in terms of estimating the total effect. And there is even a recent proposal by Henkel et al. That says there is this unique set that is going to be the most efficient estimate in this total effect. But nonetheless, as I will show that the G regression would still be no less efficient than that. It would also include other proposals, including recursive regression by this Nandy, Malush, Richardson paper, and on the same paper, some estimator based on Cholesky decompositions. So I'm going to show you this result that basically supports what I said, that the common characteristic for all those estimator is that they can be represented in this form. They are just differentiable consistent estimators of tau that only depends on the sample second moment. So I'm going to restrict myself basically to a smaller class of reasonable estimators that is only depending on the sample second moment. Then for this class of estimators, I can show that my proposal, this G regression estimator, is no less efficient than any one of them. So for any estimator from this class and for any fixed A-dimensional vector, you can show the asymptotic covariance. So ACOV means asymptotic covariance. I should say asymptotic variance. Sorry, there should be asymptotic variance. Asymptotic variance of this inner product is going to be no less than the asymptotic variance of my estimator under every law following a linear structural causal model with independent errors. So to establish this, then we, so this is not typical standard semi-parametric efficiency theory. This is rather a theory for a constrained set of estimators rather than the set of all regular estimators. So to do this, we have to homebrew a kind of a particular efficiency theory that entails basically establishing an efficiency bound for this class T and then show that our estimator achieves this bound. So I don't have much time, but I can quickly run over the basic idea that suppose you only have univariate treatment. The first thing to do is to get a handle on this otherwise obscure object of sample covariance. So I can introduce some extra edges in this G. So basically, I'm going to connect for each bucket. I'm going to fully connect all the previous buckets to this bucket by directed edges. So I'm going to call that graph as the saturated graph G bar. So in the graph G bar, every bucket is connected to every other buckets downstream. Then if you take the regression coefficients under the saturated graph and also the covariances for the residuals, then this basically establishes a diffeomorphism for any positive definite matrix. So for any positive definite matrix, I can obtain those regression coefficients and error covariances. And for every regression coefficients and error covariances, I can reconstruct a matrix that is positive definite. This is a diffeomorphism. The map and the inverse map are differentiable. And this is a generalization of another result from Dorton. Then I'm going to rewrite our estimator because it's a differentiable function on this sigma n. I can rewrite them as the differential functions on these coordinates, on lambda k's and omega k. And here, lambda kg, meaning those edges are already present, and lambda kg complement, meaning the new edges I introduced. Then I'm going to use consistency of the estimator to establish that there are certain conditions imposed on the differentials on the partial derivatives of this delta of tau hat with respect to the three coordinates. Basically, with respect to the first one, it is determined because it has to be consistent. For the third one, it's also determined, it has to be 0 actually. But for the second one, it could be free. Now, I'm going to compute the asymptotic covariance for this coordinate, the first set of and the second set of coordinates using asymptotic linear expansions. And finally, not finally, and then by delta method, I can write down the asymptotic variance for this tau hat basically as a sandwich form. I have already computed the guy in the middle. And for the two breads, for pieces of breads, I already know that the first set of coordinates has to be determined by this consistency condition, but the second set of coordinates are free. So I can, this is a quadratic form, so I can maximize over the second set of coordinates and get this upper bound. And finally, we have to verify this regression estimator achieves this upper bound. That's it. It turns out that these asymptotic covariances among the coordinates have some special Kronecker structures that would be useful in verifying the dual regression estimator achieved this bound. Okay, so I don't have much more time, but just quickly, this is a simulation study that I generated a graph of 50 vertices. The graph is sampled from some Erdős-Renyi ensemble that the errors are Gaussian. Then I'm asking two estimators to estimate the total effect. Y is some random vertex chosen, and A is some set of vertices chosen randomly as treatments. Then the cyan one is our method. The red one is the optimal adjustment set I just mentioned. That you can, the left panel is when I tell the algorithm to use the true graph. The right panel is I tell the algorithm to use the estimated CPDAG. You can see that in both cases, our estimator dominate theirs. For other errors, for T student T errors, well, if you use an estimated DAG rather than a true DAG, you basically need more sample size for this effect to kick in, but basically the efficient story still holds. Okay, the brief summary. So this is our proposed pipeline. So under causal sufficiency, you have some observational data. You use your favorite causal discovery algorithm to learn the CPDAG. Then you add your background knowledge, introduce new orientations, and you get the MPDAG. If the effect is not identified, you run the algorithm I described to enumerate a minimal set of all the possibilities. And for each one of them, I propose an efficient estimator, or efficient to some sense, then estimate every possible causal effect. All right, I will conclude the talk and accept questions or comments.
Thanks, Richard. And any questions for Richard? And I think actually Thomas typed one question in the Q&A sections.
Oh, I can't see the Q&A somehow.
Okay, I think, do you want me to read it out?
Oh. Yeah.
Okay.
Yeah.
Okay, or maybe I think I can just unmute. Let me try to unmute Thomas. Okay. So Thomas, I think you're unmuted.
Yes, can you hear me?
Yes.
Yes. Yeah, so Richard, very nice talk. I just had one question about the point where you were looking at the MLE under the Gaussian model. So about slide 22.
Yes.
I just had one really simple question about this, which is, so you're writing the model as a chain graph. I got that part, but it still is the case that we're dealing with an MPDAG. So doesn't that mean that we know that within the set of graphs there exists at least one way of replacing undirected edges with directed edges? In which case, that would and turn it into a DAG? In which case, isn't it unsurprising that we have the MLE in closed form?
Oh.
Sorry, can I interrupt for a second?
Sure,
Hi, Thomas.
Sure.
Hi, everyone. So I think, so let me see if I understand this correctly. So I think you're saying we know that the effect is identified. So therefore, why don't we just kind of pick a DAG and run this recursive thing within a DAG? Or is that what you're asking?
Yeah.
Yes, so you could do that, of course. But because you don't know essentially which DAG is the true DAG, depending on whether you choose the correct one, you might get something more or less efficient, right? So of course, if you picked the correct DAG, then your estimator from that case would be the most efficient one. But if you choose a different one, you might not end up with kind of the most efficient estimator. So this, the concept of like using buckets instead of nodes is just to say, well, with the current amount of information that you have, this is kind of the best you can do.
But in terms of the statistical model that's represented by, say, the graph on slide 19. So, yeah. I mean, if you, I'm trying to understand, if you were to replace the, I mean, isn't the point of your theorem is that it doesn't matter what way I replace the edges, I'm still going to have.
Yeah. Maybe that's another way of explaining it. Why we have a simple MLE.
Okay.
I don't know. I think I use this restricted property to prove that, but I think it is a valid point what you said, that you would expect that there exists a closed form MLE. Maybe, is that closed form? Has to be?
Any DAG, if it's a DAG, it will be closed form.
But you also have zero restrictions on the lambdas, but I guess that doesn't add any difficulty. But I don't know. Actually, I'm not sure that's going to be closed form. But you're right. That might be a simpler story for the MLE. But
I mean, just the last question, because probably other people have questions. But just going to the, I mean, with the bucket decomposition, if I'm understanding what you're doing, at least in the Gaussian case, you've got a parameterization, but and you want to keep the red edges present.
Yeah, yeah. Mm-hmm.
But I guess, the blue parts, I'm free to reparameterize in any way I want. Am I not?
Yeah, you are. Yeah, you are right. I think you are right. Yes.
Okay. Okay, that's fine. Sorry.
Maybe, yeah. I guess that's a good point. Maybe another explanation why that the surprising fact that the zeros induced by the blue parts doesn't matter. Okay. Yeah.
We talk about it offline. Anyway, probably other people have questions. But I have one other question if nobody else has a question. Right?
Sure.
Which is just in terms of learning. So you've done stuff on, at the beginning you sort of set it up with, well, I'm trying to learn the graph. Well, you know, that we try to learn the graph up to an equivalence class.
Right.
And, you know, in some other work, including, you know, work you did with me, you looked at statistically coming up with procedures to try to work out what is the true graph, or, you know, select a graph based on conditional independence. So have you thought about tying the whole thing together?
Yeah, I mean, that could be a longer pipeline, but I would say that probably would be more sound by incorporating the additional uncertainties in terms of estimating the graph itself, yeah, than just using the point estimate for the graph. Yeah, that could be something.
Thanks.
Is there any other questions?
Just one quick question. I think about a bucket. So when when you are trying to estimate the parameter tau, it seems to me that you say suppose the A is in the bucket J, and then the Y is in the bucket, say the J plus M. So then you actually only need to use the sequence from J, the bucket from J to J plus M, that the bucket containing A all the way to the bucket containing Y, right? So the previous bucket probably won't have any effect on that, right?
Yeah. Well, it boils down to the regression problem of
right. I think
regressing every bucket down the set of external parents. Yeah.
Mm-hmm. Okay. Yeah.
But the later thing is just using this thing as an instrument to prove this efficiency by establishing this diffeomorphism. But,
I see. Mm-hmm. Okay. Other questions for Richard? If no other question, then thanks, Richard, and thanks everyone for participating, and happy long weekend.
Yeah. Right, I'll stop sharing.